right, good morning, everyone. So today, we'll be talking about Chapter 14, which is indexing. So a brief overview of the concepts. We're going to start off with the basics. What is indexing? Talking about ordered indices, talking about B+, tree index files, hash indices, multiple key access, and wrapping up with how we actually do it in SQL. All right, so just to kind of let everyone know, I was looking at the schedule. Honestly, I think the stuff from today is plenty to talk about indexing. So how would you all feel if we just did a quick little lab of indexing where you just made an index or two and compared the times? And then after that, you just had a project workday on Thursday. Does that sound good to everyone? Because really, I think the stuff today is plenty to know about it. It's probably more than enough, quite frankly. Anyone agree? Basic concepts. The biggest reason that we're going to use indices is to speed up processing. And if we think about it, speeding up processing is a vital task because let's say that we have local infrastructure. Is the amount of computational power that we have fixed or variable? It's fixed. You know, the instructions per cycle, once you purchase the hardware, that doesn't change, very likely. Not to say that it can't, but for the most part, it doesn't. All right? Because you can certainly overclock and that sort of stuff. But in general, you'd want to avoid overclocking enterprise hardware. All right, a lot of reasons. Number one, reliability. Okay, so as you overclock, a consumer CPU, who's overclocked before? Ben, what overclocks did you get? Yeah. Okay. What processor was that on? Uh, 5600X, you said? 2600, okay. Was it an X or not? Just 2600. Not bad, though. Okay, so AMD, especially on their consumer line, they don't lock the multipliers. So that means you can do what? Overclock it. Exactly right. Okay. In enterprise gear, generally speaking, your capacity is going to be fixed, though, because we talked about the longevity of the hardware, the reliability as well. Because let's face it, if your computer makes a slight little computational mistake, 1 in a billion chance, that's not a big deal, is it? What if it's a server? 1 in a billion a chance you want to take? Probably not. All right, what are the other disadvantages to overclocking? What about heat generation? Okay. A lot of times, the heat sinks inside of servers aren't necessarily going to be the most robust things ever. Okay, not to say that they're terrible, not to say they can't handle full load all the time, but overclocking, you're certainly going to be experiencing where the amount of performance you get relative to the amount of heat you're generating at the marginal unit is going to be much worse. Okay, I'll try to draw that out on the board here. If I can find a marker. There we go. Okay, so basically, think about it like this. This is performance. Okay, it's going to be relatively linear. However, when you start looking at heat, okay, it's going to be going way up as your performance things. Does everyone understand that? So if you're here with performance, you may be up here with heat. And that's not good. You have a server room. Do you have one physical server in it very likely, or do you have many? You probably have many. Okay, so if all the servers are up here, you may even run out of air conditioning for the room. It's a serious consideration. Might sound like a joke. Not a joke. All right? So, we want to increase the speed of processing without increasing the speed of our hardware. We do that with indexing. All right. It's also going to increase the speed of data retrieval. Why do we need to retrieve data? Exactly right. The whole point of collecting data is to use data. Okay? So one way we can do this is with a search key. Okay, the search key is simply going to be the column or columns that we use to retrieve records with. So that's what we're going to be doing next class. Like I said, I don't really see a big reason to cover chapter 24. I think after today, I think you'll agree. Okay, so we're just going to be doing a quick little exercise. We're going to be creating indices and comparing the processing times with the indices and without the indices. And we're going to see, is it an effective indices or not, or index or not. Okay, you also have an index file. Okay, so the index file is simply going to be a basically collection of the records that you have for the index. Okay, and the idea here is that your index should be smaller than what you're indexing. That is to say, it should be smaller than the original file. Okay, so the original file is the raw data. Does everyone understand that? So, indexes should speed up processing. They should reduce storage costs. Basic concepts. You have two major types of indices. All right, these are important. Make sure you're taking notes if you don't know this. All right, you have ordered. Okay, as the name ordered would imply, there's an implied sequential order. Okay, it can be 1 through n, or it can skip around. All right, but there is some defined order. In contrast, you have hash indices. Okay, in a hash indice, what you're doing is you're not indexing with existing columns. What you're doing instead is using a hash function, and you're indexing the hashes. Talked about that a little bit already. So what makes a good index? We talked about processing speed. We talked about efficiency. So those are obviously the main two. But when you're talking about processing, there's a lot of different types of processing. So for instance, you have insertion time. An index should, theoretically, speed up data insertion. Now in practice, does it? We're going to talk about that. Deletion time. All right, if you're using a sequential index, it's not going to speed up deletion at all. All right, because it's going to slow it down instead, because it's sequential. So if you delete something, what does that mean about your index? It means it has to shift everything, correct? So that increases the speed that it processes the deletion or decreases it? Decreases, exactly right. Because it's having to do additional tasks it would not otherwise have to do. Does that mean that indexing is bad? No, this is one possible disadvantage with one particular type of indexing. Okay, also space overhead. Now, if you don't have an index, you have raw data, right? Is everyone with me? If you do have an index, do you still have the same exact raw data? Yeah, you do. So indices are not there because they're going to allow you to not store certain pieces of data. They're there to make sure you can access it efficiently in as little time and processing power as possible. Okay? So what you're really looking at is how efficiently does the index store itself? Does that make sense? Now, in some cases, indices can save you space. For instance, let's say that you had candidate keys inside of a table. All right, so you have your table's primary key, and let's just say hypothetically every other column is a candidate key. Okay, so a candidate key, of course, meaning that it could be the primary key. So hypothetically, you could use an index to remove that. That's an unlikely case because you probably wouldn't be having redundant information in a table anyways, but if you were to, that's a case in which you could potentially see an index. Could you do that without an index, though? Definitely. Does everyone understand that? Okay. You can normalize without an index. I'm just saying you could hypothetically be in a situation where you used an index to normalize. It's rare. So you're looking at how much extra space does the index take up. Let's talk about ordered indices. Okay? So really what we're talking about here is we have an index and we're going to be using the order to determine where stuff is inside the table. This is talking about the logical storage, by the way, where it actually is. Okay, so when you're putting in select statement into SQL, do you really need to know this to do the select statement? Do you actually need to know where something is logically stored? Okay, why not? Exactly right, Ron. Okay. Whatever SQL implementation you're using is going to automatically handle a lot of this. But does that mean you shouldn't need to know about it? You may have a different opinion, okay? I think it's good to be aware of this. Because if you can save your company processing, you're making your company more profitable, right? Who likes profit? I should see every hand up in here. Your business majors, all right? I love profit more than a lot of things in life, all right? I'll let you make of that what you will, okay? Let's talk about different types of ordered indexes, or indices. You have a clustering index, okay? And this is going to be the primary type. Okay, what you're doing is you're having your search key, and it's going to be in sequential order. So sequential, of course, meaning sequence. So this is saying we have the order defined, and the search key for a clustering index, by the way, is going to be an actual column inside the database, or inside the table, rather. All right, then you have your secondary index. Okay, so instead of having the search key being the sequential order, the search key is different from the sequential order. Okay, we're going to see examples of this in a little bit, so don't get too caught up on the definition. But just understand that it's secondary. If it's secondary, it means that it must have the clustering index to exist. Does everyone understand that? Okay, and then finally, you have an index sequential file. Okay, so all this is, it's just a sequentially ordered file. All right, and basically, you're doing clustering on the actual search key from the clustering index. So with pretty much any of these, you got to have a clustering index. All right, pretty basic stuff. Two types, though. You have dense index files. Okay, so with a dense index file, what you're doing is for every single record, you are having an index search key for that record. Okay, so look at this example down here. Okay, we have 1001, which corresponds with, I'm assuming this is like instructor ID or something. Okay, so it's a 1-to-1. So for every key, it matches with one and only one, by the way, record. Does everyone understand that? Anyone confused? Okay, so the disadvantage of a dense index file. Well, when you compare it to a sparse index file, you're going to be storing more keys. Okay, so when you're storing more search keys, does that take up more or less space? More. Okay, because when you store more things, it takes up more space. Ceteris paribus, of course. All right, so a sparse index file, instead of having 1-to-1, one key, many records. Does everyone understand that? Okay, so if you're wanting to find the record, okay, here's all you have to do. All right, you look at this, and you're going to go to the largest search key value that is less than what you're trying to find. Okay, and then you're just going to search it sequentially starting at the record. So if you're trying to find 1001, you're going to find the largest possible search key value. So you would go to 1000, or this is 10,101, isn't it? Okay? I apologize for that. So you would go here, and because it is starting sequentially, you would start right here. Now, if you were doing that, you would find it immediately, right? Let's say that you wanted to find 58,583. Which one of these are you going to go to? Exactly right. And then, correct me if I'm wrong, but you would start here and you would go sequentially until you find this value right here. That's exactly how it works. Here's a question. Let's say I wanted to find 98,345. Colton, which search key value am I going to go to for that? Okay, so I'm going to go to this right here, and then what do I do to get to here? Exactly right. Okay, I think everyone understands this. Does anyone not understand it, though? All right, dense versus sparse. So sparse takes up less space. If you're storing fewer things, we're assuming we're not dealing with deduplication or anything like that. Storing fewer things, it takes up less space. All right. There's also less maintenance involved, because if you go back to this, if you have fewer keys, unless one of these updates, then you don't have to update anything, right? So you're only updating the keys. Whereas if you look at this, if any of these update, we have to update a key, search key. So is that a big advantage? Depends on how often you're updating, right? Okay, but when you're using sparse, the processing power is going to be substantially higher that is required, because you're not just finding a key in sequential order. You may then have to do an additional step of searching sequentially from the point of the key to wherever you're going. Does that make sense? So which is better? It's a trick question, right? Depends on the circumstances. If you have data that's seldom updated, dense is probably better. If you have data that's updated quite regularly, sparse is probably better. If you have data that you're needing to constantly query through, which is going to be better? Dense, because it's faster, more efficient. All right, for processing at least. Okay, then you got secondary indices. So a secondary indices is basically an index of the index in a way. Okay, so what you're doing, you're pointing to the bucket. So this is a bucket over here. And the bucket is pointing to the actual value. All right? Now for this, it must be dense, because for this relation to work, okay, you have to have a one-to-one. Does that make sense? So let's take a look at this. Okay, 40,000 corresponds with this bucket. This bucket corresponds with 15,151. All right, is that complicated? Probably. What's the good news about this? As a database administrator, even if this is your job, do you really have to know which bucket is pointing to which record? You don't. Okay, because that's going to be handled by the SQL implementation. You should understand that there are buckets involved. Okay? But you don't have to worry about the pointer. All right? That's all handled automatically. So personally, I don't see a big reason to spend a whole lot of time talking about it. All right, multi-level indexing. So let's say that you wanted to do a dense index. Okay, and let's say that you had $15 billion records. That's not a small number of records, is it? It's quite large. So 15 billion records, and you're doing a dense index. Assuming you're indexing on one column, how many search keys would that be? 15 billion. Reckon that'll fit in your CPU cache? Why not? It's a huge number, right? 15 billion. Okay, that's probably not going to fit in any CPU cache. All right. So, why do we want to fit indices in cache? Okay, well, number one, cache is far closer to the processor, which means lower latency. Now, that's not necessarily a huge deal, all right, because, latency, once you have a transaction moving, it doesn't really matter that much, does it? At least in most cases. Okay? So we don't really care about latency. What other advantages do CPU caches provide? What do CPU caches do that RAM can't? So with a CPU cache, it's going to be a lot faster than any RAM. Okay? I'm not talking about like comparing some, Pentium 2 cache against like, DDR5. Yeah, I mean, the DDR5 would probably be faster than the P2 cache, but we're within the same generation. CPU cache can be way faster. Have a higher or lower tolerance for read writes than RAM. CPU cache is much higher. Who's ever heard of a broken CPU? Okay, when it happens, is it because the cache is not functional? Not likely. Okay, I've actually never heard of that in my life. All right. Who's heard of broken RAM sticks? It's a more common problem. All right, when you do hear about a broken CPU, what's likely the issue? Probably some sort of a broken pin of some sort. Okay, so that's probably what's more likely taking place. Could also be really intense amounts of electrostatic discharge. I've never actually heard of a cache file, or not a cache file. I've never heard of a cache just straight up breaking. Not to say it doesn't happen. I'm sure it does in data centers. Just never heard about it personally. All right. So large indices do not fit in memory. We talked about why that's a problem. Because you don't just want to have it in memory, you want to have it in stuff faster than memory. All right, cache files. Not cache files, caches. Would it make sense to put stuff in graphics memory in a lot of cases? On a server, probably not. Why not? Well, most likely, servers have incredibly weak graphics processors. Okay, so understand that the Intel Xeon line does not, and to my knowledge has never included an iGPU. All right, so they have, if anything, they're likely to not have a very powerful graphics processor. Probably just some VGA compatible card that slots in, if they're even using graphics at all. Okay, Let's face it, most servers don't use graphics. No, that's not to say there aren't high-end graphics cards designed specifically for servers. Think about the Quadro line. But that's for a very dedicated set of tasks. It's not for general purpose computing, is it? All right. No one's buying a Quadro for basic server output, video output, I mean. So, how do you solve not being able to fit an index in wherever you're wanting to fit it? All right, well, simple. Okay, you can construct sort of a multi-level index. And all you're doing is you're making an index of your index. Okay, so the sparse is going to be in the outer index. You have a sparse index of your index. All right, and then you also have the inner index, which is going to be the basic index file that you're working with. Okay? You can create as many of these layers as you want. So the end goal is to get an index that will ultimately fit inside of your memory. Now, the more layers you create, the more time it takes and the more processing, rather, it takes to do updates. All right, because if you have 15-layer index, you make an update. Is it possible you may be updating all 15 layers? That can be fast or that can be slow. Very slow. All right, and like it says here, you must update anytime you're inserting or deleting. Very slow. Here's what it looks like. All right, so you have your outer index. It's going to feed into the inner index, which is then going to feed into additional indices. All right. So if you're wanting to index on multiple keys, that is to say, if you're using multiple columns for an index, how do you actually do that? Well, it's quite simple when you're creating the index. Literally, all you have to do is just say create index, and then you would name it, and then you'd say which column. Quite simple, right? SQL's cool like that. But what this is called is a composite search key. Okay, so in this example, we have an index on the instructor table. Okay, so we have a table called instructor, and we're creating a multiple key index on it, which is using both the name and the ID of the instructor. Okay, and basically, it's going to be sorted lexicographically. All right, it's a fancy way of saying it's sorting it with two things. Okay, so we have both the name and the ID. So see, here's the example. All right, we got 3 people named John. Okay, so what's happening is it's sorting first by the first column, which is what? The name. So John comes before Peter, does it not? Okay, if you were to sing the ABCs, you get to J before you get to P. All right, take my word for it, or you can sing the ABCs. It's up to you. Okay, and then you're sorting by the ID. So you see we have 1,200, 1,300, or 13,000, 13,000 again, and then you're having the 11,000. So again, look at this comparison. This John is greater than this John. This Peter is greater than this Peter. Okay. Lexicographical order. Okay. So, good news about this. You can query on either the name, the ID, or the combination. So what this really allows you to do is to have the ability to do multiple columns that are going to be more quickly queried. Now, what's the disadvantage of this? Think back to what I said earlier. If you're storing more information, it means what? More storage, more processing. What else? Takes longer to update. So, multiple keys make sense in some cases. Those cases would be if you had multiple columns that you were constantly querying based on. Then an index makes sense. Specifically, a composite search key index, which is also referred to as multiple key index. In pretty much any other case, does this make any sense? No, not really. Okay. Let's talk about the B plus tree. Okay. So what we're doing here, we're basically just forming a sort of a tree. Okay. Not too dissimilar from a decision tree. You guys covered decision trees in your analytics classes? What's a decision tree? Exactly. All right. So it looks something like this. Okay. Student, yes, no, and then you have another question, blah, blah, blah. You get the idea. Basic decision tree. Okay? So, all of your paths, all the way from the root up to the leaf, okay, going to be the exact same length. That's a beneficial concept. Okay, because that means that it's automatically sorting everything. That's what that's saying. Okay? Each node, other than your roots or leaves, okay, has between n over 2 and n children. Okay? So again, that goes back to the idea of these are all the same length. So if they're all, if everything in here is the same length, okay, what this is really saying is that we're between n minus 1 divided by 2 and n minus 1 values. All right, and if you think about it, that makes a lot of sense. Okay, because throw me an integer. Okay, so 5 minus 1 equals 4. Does that make sense? Now, if we were to say 4 divided by 2, what does that give us? 2. So in that example, we'd be between 2 and 4 for the number of values. Now, most likely that'd be 3, wouldn't it? Okay, so let's talk about some unique cases. Now again, are you likely as a database administrator to ever have to deal with any of this? No. Okay, so first of all, there are easier ways to do things that provide you with the same advantages that a B plus tree is going to be giving you. All right, but let's talk about these anyway. If the root is not a leaf, okay, it's going to have 2 children. All right, and that's a minimum. Okay, so basically, I don't really know of a case where a root would be a leaf. But as long as you're dealing with something other than a leaf, you're going to have at least 2 children. Okay, if the root is a leaf, okay, so this is the case where you would see that, okay, so there's only one node inside the tree, which is something where you wouldn't bother to make a tree for, right? If you had only one thing, why on earth would you put it in a B plus tree? Can anyone think of a good reason? I can't either. All right, but that's going to have between 0 and n minus 1. Okay, that is to say it's going to have 0 values. Here's what this looks like. Okay, so you have your root at the top. Kind of the opposite of how we think of a tree, isn't it? Okay, trees don't grow from clouds, do they? Where do trees grow? In the ground. Okay, it's not a very difficult class, is it? Imagine if I had an exam and I put that on there. I like to think everyone will get that question right. Okay, so you start with your root, and then you're going to form nodes. Notice these nodes are all what? They're the same what? The same size. Okay, so you have your different stuff inside of the root node. It's going to break off, And basically, you just continually break off until you don't. And then, of course, all this information will be compiled from your SQL implementation to a usable table. Okay, let's talk about the node structure a little bit more. Okay, so basically, you have K sub I. All right, those are going to be your search key values. All right, P sub I, your pointers to the children. Okay, so for everything but the leaves, of course. Or pointers to records. And you can also, of course, point to a bucket of records. All right? And basically, they're going to be ordered where K1 is going to be less than K2, and so on until you get to K sub n minus 1. That's going to be your highest. All right? So why would you actually use a B plus tree? Well, in some instances, it may speed up processing. I would make the argument that an index will do the same thing and be much easier to understand. All right? Feel free to disagree. In fact, you could view every single thing you ever wanted in life with a B plus tree. I really don't care. It's your life. Okay? Is that fair to say? So, talk about the complexity of updates. The more complex an update is, ceteris paribus, it's going to have a higher cost. Okay, and the cost is really composed of two primary things. Number of CPU cycles that it takes to process, as well as the input-output operations. Now, when I say input-output operations, what am I most likely referring to? Starts with a D. Okay, not data. Let's play Hangman. All right, someone guessed ATA, so that's going to be that. Okay, you said E? No E. Take a guess. Said U? No U. It's almost hung, it is an I. What is the answer? Talking about input-output. So think about where that would be stored. That's your hint. Said M. He's hung. Okay. Disk. All right. So you want to reduce the amount of disk operations that you're doing. There's a lot of reasons for that. Number one, if you're using pretty much any type of disk and you continually do operations on it, what happens to the amount of heat generated by the disk? Does it increase or decrease? Well, you know you can't decrease the amount of heat something generates, so it's going to increase. Okay? Well, I'm not going to say you can't. You can certainly undervolt and that sort of stuff, but you get the idea. Okay, so for the most part, anytime you're doing an update, you are generating heat. All right, if you live, you're generating heat. Does everyone understand that? Basic thermodynamics. What else? How about wear and tear on the disk? We're talking about, I don't remember which class. sure you guys were in it though. Is there a disk that doesn't wear down over time? Any type of disk. I'm not even talking about performance degradation. I'm talking about if you continually write to a disk, is there a mean time to failure? Is there a disk that doesn't have that? Wouldn't it be great if there were? But there's not. So, in the context of an enterprise data center, I mean, sure, wearing down disks is bad. Is it not a bigger problem, though, to lose the data on the disk? Probably. You mitigate that with what? I hope you all know this one. Backup, exactly. Okay? So, we talked about disk operation. That's what we're talking about with input-output. So we're both processing and storing. Does that make sense? Okay. So, basically what we're seeing is the worst possible case of deleting or inserting an entry. It's going to be this calculation right here. Now, luckily for you all, you don't have any tests, do you? Okay? So I don't see a reason to go over that too much because guess what? It's handled automatically. So it's the worst possible case. But you're unlikely to ever reach that worst possible case because internal nodes are going to serve as a buffer. Okay? So that buffer is going to reduce the number of input and output that's going to take place. Beyond that, okay, most of the time, whenever you're inserting or deleting something, it's only for a single leaf. It's not for the entire tree. Okay, if it were for the entire tree, this is what you would see. But that's highly unlikely. Not to say it can't happen, just that most of the time, instead of updating everything, you're just updating a particular leaf. Let's talk about non-unique search keys. Search keys that do not correspond with one and only one thing. Okay, right off the bat, I'm going to go ahead and say it's probably a bad idea. Is it not? But you can use them. Okay? So one example. Okay, you have buckets. Okay? And they're going to be on a separate block. That's a really bad idea. Even the book says it's a bad idea. Okay? So basically, you're just having those buckets be corresponding with different things. All right? And you're basically having your different pointers there, and they're corresponding to a key, but as you increase the number of them, you're going to have additional ways to handle the list. Now, that's not to say that you personally have to have this, because what have I said several times today? The SQL is going to do this for you, okay? But you may have your complexity be linear, okay? This right here is saying that as stuff gets more complex, there's more processing power. Now, even with that as a con, is that really that big of a con? It's not. All right? Who's played Fallout New Vegas? Patrick, didn't you say you played Fallout New Vegas? Tell me about the great cons. Okay? So the great cons. All right, they're a group in Fallout, and then they're also in, I think, Fallout 2. Maybe Fallout 1 as well. All right, why did I mention the great cons? I want to tell a pun about it's not a great con. All right, get it? Because I said this is not the biggest con. If something scales linearly, that's not that bad. Who thinks it's bad? Okay, it's not. That's your worst possible case. However, all right, it's going to take a lot of extra space. Okay, so you're not necessarily having a ton of overhead here, but there's still some. And that's not going to cost you anything extra when you're running queries. Okay, it's going to take extra overhead storage though for your keys, which we know that's true of any index, right? Key storage is not free. There's no such thing as free lunch. What does that mean? Everything does, even in technology. No, that's not actually true, is it? You can make a really strong argument that deduplication is free lunch. But that's not a physical thing, is it? All right, and also, deduplication implies there has to be stuff in common between your files. Most of the time there will be. Will there be 100% of the time, though? Is it possible to have files that have no possible deduplication ability? It's going to be quite difficult to do, but it is possible. All right, but we're not talking about that. Okay, so the idea is that this is going to provide us with a simpler way to do insertion and deletion. And when I'm talking about simple, I'm not talking about it's easy for you to implement. Any of this stuff is easy to implement, okay, because SQL handles it all. What this is referring to is that it's going to be less processing. So we're talking about fewer CPU cycles, fewer input-output operations. That's very important. Indexing issues. Okay, indexing is not perfect. We already established it costs extra storage to do. Not a whole lot extra, but extra nonetheless. Okay? So if you have a record and you need to relocate it, and you have secondary indices, you're updating multiple things. Okay, so again, you're having to update those secondary and those primary indices. That's going to be a little bit slow, is it not? It will be. Okay? So if you have a node split in a B+ tree, okay, what you're really doing is you're having to update everything along the way, which is going to be pretty slow, and in terms of the input-output, it's going to be a lot. Okay, so what you can do is use a search key instead of record pointers. All right. Now, it's going to have fewer updates, however, it's going to be more storage. So it kind of makes sense. Everything has an advantage and a disadvantage today. Most things. If you think about it, you had advantages and disadvantages showing up for class, didn't you? What's the advantage? Okay? Yeah. You know? You guys remember the Ty Lopez commercials? What's he all about? Other than scamming people, what's he all about? That's a joke, by the way, for the recording. Okay, so he had his Lamborghinis in his garage. You guys know what I'm talking about? Got his bookshelves. Went down to Goodwill and they had a 10-for-1 book day, didn't he? I'm joking. All right, these are all jokes. So, pros and cons. What are the cons to coming to class? Okay, in general, not this specific class, of course. Can you get bored? You probably get bored in class. Been a student at one point. Class can be kind of boring. What else? Okay, you're not out there doing other stuff. You're not out there hustling, are you? You're in here. All right. What else are you not doing? Okay. Well, you're in here not doing anything else, presumably. All right. So, indexing on Flash. Flash, of course, being another name for solid-state storage. Now, is all solid-state storage faster than all magnetic-based storage? Who says it is? Who says it's not? It's not, that's right. Ton of slow flash storage out there. For example, anyone ever use an eMMC drive? They're pretty horrible. All right. Anyone ever use like a class 1? I think this is for SD, micro SD card, if I'm not mistaken. Anyone ever use one of these? They're not very fast either, are they? What about like an old USB 2.0 flash drive? Is that going to have fast input output? No. So don't get in the mindset of thinking it's going to be faster no matter what, because it won't. Okay? Now, what will be faster in most cases could be random input-output. And what that really means is, with any sort of spinning storage, you're having to make sure that the reader, be it optical, be it magnetic, is in the particular location that you want it to be. And that might take a couple revolutions to get to that point, right? Okay? It is quite possible that's wasting time. With solid state storage, you don't have that. Okay, there are no moving parts. So there's no moving parts. What does that mean then for your random input-output? It means it's not going to be substantially different from sequential input-output, right? Okay, does that make sense? So another way to think about this is your writes are not in a particular place. Okay, like I talked about, I don't remember which class, but I was talking about in one class at some point. Okay, we don't do what to solid state media? Starts with a D. Defragment. Exactly right. Why not? Does it make any difference for reading or writing where you're reading and writing? Very little, if any. Okay. A horrible idea to defragment a solid state drive, because all you're really doing is you're increasing the read and write cycles on the drive. Okay. So, obviously, whenever you're having a paged file, all right, you want it to be as small as possible. Pretty obvious, right? Okay. So basically, what you're doing is using write-optimized tree structures. So instead of being optimized for reading, what these are optimized is for writing. Because we've established that SSDs, ceteris paribus, are going to be faster than most spinning disks. I'm not saying 100% of cases. I mentioned some cases that's not true of. But if you're in an enterprise environment, okay, can you think of any enterprise environment who has eMMC storage for their NAS, or better yet, their SAN? Has anyone ever heard of that in their life? Okay, I haven't either. So you're not going to face a case in which it wouldn't be faster in an enterprise environment. Now, let's talk about the main memory. Okay, that is to say, we're probably talking about your RAM. Doesn't have to be your RAM. Could we possibly be referring to video RAM? We could. Unlikely, but it's possible. So, in almost every case, you're going to have RAM that is faster than your solid state drive inside the system. Much faster, by the way. Okay? So it's going to be less expensive to update because it's faster. But it's better to do it where? Or is it better to do than even memory? Cache. All right, Ben, you think cache is king, don't you? Okay, that's a joke, by the way. Kind of a play on a common saying. Cache is king. What do I say instead of that? Okay, I say I am king. Now that's a joke, but all right. Cache is king, though, for certain tasks, is it not? It's not a financial statement, just in general. Okay, so let's talk about hashing. So really all we're doing here is instead of using a key, a search key, which is going to be a column, we're just hashing stuff and using the hash file. Now the main advantages here is that we're going to have the same size hash for everything. And if you have particularly large columns, you know, this is going to save you a little bit of space, isn't it? Okay? So basically, let's think about it like this, okay? You're having your hash function, we're defining it as H, and it's going to be from all of your search key values K to the bucket of B. All right. All you're doing is using a hash instead of a key, search key. Does that make sense to everyone? Here's what this looks like. Okay, so you're using hash file organization where you have, in this case, 8 different buckets. All right, buckets 0 through 7, using department name as your key. Okay, so you're putting everything into buckets, and then basically what you're doing is you're having a hash associated with department name. So department name is going to be this column right here. Does that make sense? You're just hashing that. Simple, right? 2 types. You have static and dynamic. So static hashing, you're going to have a fixed number of buckets and also a fixed size of buckets. So as your file is going to grow, you're going to have fewer and fewer things, or you're going to have a smaller and smaller percentage, rather, of stuff included within inside the bucket, which is going to make your performance slow down. Okay, and also, your space is not going to be used well, because let's go back to this example here. Are there empty buckets? Where? 0 and 7. All right, these are both empty. Is that a good way to use space? Why not? Okay, so like Nick was saying, it's not good to have empty buckets because you're just taking up space for no reason. All right, so how do you get around that? Okay, we'll use dynamic hashing. Okay, so I personally wouldn't recommend even bothering with static hashing. If you're going to use hashing, which in this example, let's face it, does it make any sense to use hashing at all? When you're basically hashing department name. Does that make any sense? Based on the data we see. Who says it does? Who says it does not? Ron, why do you say it does not make sense too? So we're hashing the department name, and we're using that as the key, as opposed to the actual department name as the key. Apodaca, what you think? Well, the empty buckets are a big problem, but that's just because it's a static hash. Does it make sense to use hashing at all for a department name, assuming these are represented as department names? What do you think, Nick? Okay, so what you're saying, I think, is that because none of these are particularly long names, all right, the hash is going to be substantially longer than the name itself. Is that what you're getting at? Well, that's exactly why it doesn't make any sense. Okay? So this is just an example from the textbook. Don't think it's an example I came up with. Does that make sense? But you can certainly still do it. All right, so let's talk about dynamic hashing. 3 major types of dynamic hashing. Okay, so the first type, okay, going to be we're using periodic rehashing. Okay, what you're doing here is basically on a periodic basis, you can set whatever parameters you like for that, of course. You're rehashing. You're creating new hash tables. And basically what you're doing is you're then rehashing everything within inside the tables. Now, even with various technologies built into processors like TPMs and that sort of stuff, is hashing an inexpensive thing to do? It's not, is it? So this is going to be kind of costly. Linear hashing, okay? So as opposed to having some set criteria of the periodic, okay, here you're doing it incrementally. Set whatever increments you want, yet again. And finally, you got extendable hashing. Okay, so here you're having buckets that are going to be shared. So as opposed to having everything for one bucket, you're having buckets that are going to be shared, and this is primarily going to be used for disk, because if you're using a hard disk, you don't want to be doing a whole lot of input-output operations. It's going to be very slow. Okay? So those are the three primary types. Does everyone understand them? Let's talk about multiple key access. All right, so we talked previously about having a key that's a composite key, composite search key. What did that mean? A couple different keys which come from the columns, right? Okay, so all we're doing is just using multiple columns here. Does that make sense? All right, and again, we got several different ways to do this. If we're trying to find where department name is finance and the salary is equal to 80,000, all right, we have three ways to do it. Okay, first, what we could do is we could find all the instructor names that are in finance. Okay, and then you would see which of those has a salary of 80,000. Okay, you could also, of course, find all the instructors with a salary of 80,000, and then see which ones of those have the department name of finance. Okay, and then finally, what you could do, you can just find all of the records that are in the finance department. All right, so that's basically what you're doing, and then you're just sorting out from there. Three primary ways. Really, it's two primary ways, because you got two different keys, right? Is it fair to say the first and the third are basically the same thing? They are. Okay. It's just a matter of if you're going ahead and selecting the instructor information, or if you're getting everything about the instructor for the finance. Does that make sense? So the last thing we're going to cover today is actually creating an index in SQL. Okay, up to this point, I'm sure some topics have been a little bit confusing. You have to kind of think about them for a minute. I'd like to say you wouldn't need to think about this at all, okay, because it's really simple. All you're doing is you're saying create index, then you're naming the index, and then you're saying on, and then what is the relation on. So that's going to say on which table, because another word for table that the textbook kind of uses is relation. So on the table, and then you're just saying inside of parentheses what attributes, attribute or attributes. Okay, so here is an example. Create index, they're calling it B index. They're saying on the branch table, and then the attribute they're using is what? Branch name, exactly right. Okay, you can say create unique index if you wanted to. You don't have to, but you can. All right, and if you want to get rid of an index, same way you get rid of a table. Just you drop, and then you're not dropping a table. What are you dropping? An index. So say drop index and then the index name. Does that make sense? It's just not a whole lot easier than everything else we talked about today. Now, like a quick vote. Who wants to go over chapter 24? Okay, does anyone want to go over chapter 24? Who wants to just do quick examples of indices and then have a project workday next class? I'd like to do that as well. So, just to wrap up, talk about basic concepts, talked about ordered indices, talked about Btree index files, talked about hash indices, talked about multiple key access, and we wrapped up by talking about how we actually create them. All right, any questions about anything today? That's all I got. Feel free to hang out if you have any questions. I'll be happy to take them. Also, feel free to hang out for another 20 minutes or so and work on your projects. Do whatever you want. Have a great day.